All right. That's not working so well. Oh, well, maybe it's good enough. Can you guys hear me OK? Is the microphone picking it up? No, I mean, it's just tilted forward. Apparently. There. That's better. OK. So hello, everyone. Good to see you again. Hope you enjoyed the banquet last night. Just a reminder where we were yesterday. We wanted to know what if string theory was correct, and we talked a little bit about the landscape and what that might mean and might not mean. But the idea was that regardless of what the correct notion of the landscape is, it's oftentimes the case that string theory gives you low energy degrees of freedom. These are degrees of freedom from the ultraviolet theory. They're not necessarily there to solve some problem. That's what we normally do when we model build from the bottom up. There's some problem that we're interested in. We introduce degrees of freedom to solve it. Sometimes string theory just gives you these remnants, these low energy degrees of freedom from the UV theory that are not necessarily there to solve some IR problem. And I went through a bit longer derivation than I had hoped to about non-Higgsable clusters, which are these 7-brane stacks that can carry gauge sectors that can exist for generic values of the complex structure moduli in F theory. These are quite generic in terms of some sort of counting measure, which is not the cosmological measure that we're ultimately after, but it's better than nothing. And what I demonstrated was that there's a large set of F theory geometries. And in that set of F theory geometries, non-Higgsable clusters are totally generic, and the gauge groups are quite big, which, if this is something that you should take away from the landscape, and this basic low energy remnant of large gauge sectors happens in other corners as well, then maybe you should consider dark sectors that are potentially formed out of dark glue balls and or hadrons. In some cases, you can run into issues there where you oversaturate the observed dark matter relic abundance, and the theory is ruled out. But there's a number of papers on this, and it's not really a settled story yet. But the basic point is that maybe string theory actually gives some motivation for these things. There was a lot of algebraic geometry last time, and I'm not going to do much today. So if algebraic geometry is not something you're too familiar with yet, or not your cup of tea, have no fear. The stories I'm going to tell you today aren't going to use much of it. I was hoping to tell you 4 stories. Given how long the last one took, I'm down to 3. So I'm going today to tell you about axions, and also about beyond the standard model exotics. And the basic idea just recalling the outline from last time, way back there, is that basically everywhere you look in string theory, and I'll try to quantify some version of what everywhere means, you get axions. I'll try to give you a little bit of a framework for thinking about that and some of the different things the axions can do. And in the context of weakly coupled Orianifolds, again, there's a remnant that occurs much more generally, but I'll be in this context. What you find is a connection between consistency conditions and beyond the standard model exotics of the type that has been mentioned in some of the lectures this week. So these are the 2 basic things that I want to cover, and hopefully there's more time for questions at the end than my rushed lecture yesterday. I can talk about either of these first. Does anyone want to hear about axions first? Does anyone want to hear about beyond the standard model exotics first? OK, axions wins. But I'm going to get to both of them. So let's start talking a little bit about axions in string theory.
Why isn't axions beyond standard model exotics?
Sorry, here I mean charged beyond the standard model exotics. Very good. Yeah. Axions are definitely beyond the standard model exotics. Good. Thank you. So we're everywhere in string theory here. And in particular, we want to ask about 3 basic things. Axions are good for a few different things. One, which I'm not going to talk much about, is that they're interesting inflationary candidates. So when there was lots of hope about the bicep 2 result, before there was much less hope about the bicep 2 result, though it is a wonderful experiment, the hope that these were actually primordial gravitational fluctuations that were being measured by a non-trivial tensor to scalar ratio, a lot of work on axion inflation in string theory came out, including by some of the people in the audience. And that work is really good work. Part of the story about those large tensor to scalar ratios, those large gravitational fluctuations, is that they can arise in axion inflation models with very, very large axion field ranges that are super Planckian and correspond to super Planckian axion decay constants. And so there's been a whole story that has ensued out of that about axion inflation in string theory, whether or not you can get large, meaning super Planckian axion decay constants, and also whether or not that is tied in interesting ways to the weak gravity conjecture. I'm not going to have much to say about that, but this is a very interesting story, and I'm happy to provide references. Another is that axions could potentially be dark matter. We've known this for a very long time in QCD, but there's lots of other axions in string theory that could potentially be the dark matter. Finally, when you have lots and lots of degrees of freedom, if they're sufficiently light and populated cosmologically, you could run into an issue where you get constraints on the landscape because you have too many light degrees of freedom. So for example, landscape constraints. So for example, there are bounds on the number of effective degrees of freedom, for example, from Planck, that lots of axions in string theory can run into tension with. Not going to have much to say about that either. I'm mostly going to focus on how axions arise in string theory and a little bit about dark matter aspects. OK, so all of these lectures are starting with formalism and moving towards phenomenology. And there's an organizing principle for axions that I'm just going to tell you about. The basic theme is that you have some higher D theory one of your favorite types of string theory, with some CP p-form field and a symmetry CP goes to CP plus D lambda p minus 1. Okay. And when you have this higher dimensional theory and you compactify it down to 4 dimensions, of course, these form fields can enter in the low energy theory. So if you take sigma I, a basis of HPXZ, notice I'm not even talking about which type of string theory or what type of manifold X is necessarily. If you just have a basis, then you can get 0 forms in 4 dimensions, that is, axions with a shift symmetry, from integrating these p-form fields over the sigma i's. And this gives you a 4D scalar, assuming I'm compactifying to 4D, with the shift symmetry. And this symmetry, this is exact in perturbation theory. But it can be broken by instantons. So this is the basic formalism. So what do these instantons look like? I'll mention a little bit more about them later. But for example, these instantons can give you a non-perturbative superpotential of the schematic form A, some prefactor that is a moduli-dependent prefactor, where almost no one ever computes the moduli dependence, e to the minus t, where t is some modulus field, plus dot, 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 because there could be other contributions in the superpotential. And here, A, the axion, is the imaginary part of the scalar field T. OK, so one thing to mention is that you might want to ask, what is the number of axions? This is a story that you may be familiar with. Well, I'm getting an axion for every sigma I that I have. And they'll couple in different ways in the low energy theory according to the detailed topology of the sigma i's and x. But the number of axions is the number of sigma i's in the basis, which is just h3xz. or alternatively, the third Betti number. Sorry, the pth Betti number in this case. I don't know why I wrote 3. I had a specific case in mind. OK? So this is the basic theme, and this is the story that pick your favorite type of string theory just plays itself, plays on over and over again. And so what do I mean when I say from everywhere? From everywhere, I haven't drawn this yet, I don't think. I draw the obligatory starfish thing. Right? And there's 2A, 2B, heterotic E, heterotic O, type 1, I don't know, maybe there's other corners. And in here we have M and F theory because we've moved away from weakly coupled limits. And for example, in the heterotic string, so the thing that plays itself on over and over again is the existence of these form fields. So there's the NS-NS2 form, for example. In M theory, of course, being the quantum completion of 11-dimensional supergravity that we would love to know more about, but it has the 11-dimensional supergravity fields. There's a C3 field, the 11D Sugra 3 form. Okay. In 2A, there's also a C3 field of 10D 2A Sugra. I know this is a little pedantic, but I'm just trying to make the point about how common these are. In 2B and F theory, in the 2B language, there's C4 and C2 in type 2B supergravity, which give you 2 different types of axions. These are Ramon. OK? And maybe I'll leave it there. You know, these are the main things that we've that I've been thinking about, at least. So. Yeah.
Why do we have 12-dimensional supergravity for that theory?
That because I can't write well. Yeah, that's 11. Just not clearly written. My apologies. Yeah.
B2 and type 2A and type 2B also?
That's right. Yeah, that's right. I didn't list all of them. B2, B2. Yeah, absolutely. OK. So let's now talk about so the number of axions needs some required knowledge about manifolds, right? And so in particular, a lot of these are going to be on Calabi-Yau threefolds, where X is a Calabi-Yau threefold. In M theory compactifications to 4 dimensions with n equals 1 supersymmetry, the canonical thing we consider is, do you guys know about this? G2 manifolds. So 7 manifolds. Note, 7 is not an even number, so you can't use complex geometry, which makes it a lot harder. But nonetheless, there's a beautiful story that's been coming out of the math community in recent years. G2 manifolds are 7 manifolds with holonomy exactly G2. They're the M theory equivalent of Calabi-Yau threefolds. And so if you wanted to consider that, you could consider G2 manifolds as well. Here you would be computing B3, and depending on the case, you'd be computing various different quantum numbers here, various different topological numbers. And in all of these cases, there are cases with low Betti numbers, which will give rise to a smaller number of axions. But quite commonly, there's order 100 to 1,000 axions coming from this, which, if you're familiar with this literature a bit, maybe you call this an axiverse. OK? OK. So this is the basic story. There are lots of different scenarios for how to think about axions. One that I recommend you look at is axion monodromy, in addition to axion inflation papers that are out there. Axions couple in the low energy theory, and depending on the details, they can couple in different ways and have different physical phenomena. What type of physical phenomena it gives rise to is, of course, dependent on the axion mass, right? Which begs the question, how could you potentially think about masses for axions in string theory? So let me talk about what the right thing to do would be. In string compactifications, we're often in this tension between doing the full story, that is very complicated and takes a long time to learn. And sometimes the computations are so complex that Mathematica crashes and your computer explodes long before you actually get somewhere. The tension between wanting to do that and wanting to come up with some useful, effective field theory way to think about the degrees of freedom that you have. So in full string theory, what you would typically do, depending on the context, is find all important, meaning playing an important role in the effective action, instanton corrections. So generally, you're going to have some non-perturbative superpotential where you have some sum, you have some operators out front, e to the minus qij tj, and maybe there's some other things that I'm not worrying about. And you need to determine, first of all, you don't get to choose what instantons your theory has or doesn't. You have to determine which ones it has, and that is a bit of a computation. But it's doable, and you'll generally get some sort of sum of this form. The axions are appearing in here in different linear combinations. These give rise to the axion contributions to the scalar potential. And these are what give rise, ultimately, to axion masses. This is non-trivial. So you would do that. And then, of course, you would compute the full V of phi. And I should say, there's really nice works that actually do this in cases with low numbers of moduli. The thing that's hard is if you have 100 axions and 100 moduli, this can be a very, very complicated potential. And doing the full story is out of reach right now. But people have done this for low numbers of moduli. So compute V of phi and find the masses and the minima. Find the minima and the masses. Okay. So it's a little bit impractical for large moduli. I wish it wasn't. For large numbers of axions, for large numbers of moduli, it's a bit impractical. One is a technical reason that this actually maps onto a known problem in number theory or complexity theory, if you'd like. This problem is related to solving Diophantine equations, which is a notoriously difficult problem from the point of view of number theory. But also, just as the numbers get large, the equations get very complex, which is something that you run into a lot. So if one could actually do this calculation, you would like to know, for example, if you have lots of axions in a stabilized string compactification with a large number of axions, you would like to know what is the field range for the longest axion. Is it super Planckian? Could it give rise to large field inflation? Is dark matter coming to the game, et cetera? That would be a great thing to know. And hopefully, in the coming years, one of you will really crack this. Yeah, so all of them contribute. All of them contribute, of course. One of the things that's interesting from the point of view of the string theory is that, for example, just to pick a case, type 2b, there's a distinction between whether the Euclidean D3 instanton wraps the same 4-cycle as a D7 brane, in which case it can be interpreted as a small gauge theory instanton, or whether it wraps a cycle not wrapped by a D7 brane, in which case it's not a gauge instanton. Those axions typically are not going to be coupling to gauge fields, and it's a different type of physical effect. But of course, you have to contribute all meaningful, all important contributions to the effective action have to be taken into account, including gauge instantons. All right. So you could also say, let's just take an effective field theory approach, maybe effective field theory motivated by string theory, and go that way. Yeah. Maybe just do 2 boards at a time. My iPad's getting wet. All right, back to business. All right, so that's how you would do the full computation in string theory. And I should say that depending on the context that you find yourself in, these are different types of instantons. There are string worldsheet instantons. In 2A, there are Euclidean D2 instantons. In M theory, there are M2 brane instantons. There are Euclidean D3s in type 2B. And depending on what context you're in, there are different types of instantons. But in some cases, they are computable, and you can determine these corrections and determine what the axion masses are. One of the things that's hard about that in certain cases is that they need to wrap supersymmetric cycles, which, if the dimension of the cycle is odd, constructing those special Lagrangian submanifolds, or alternatively associative submanifolds in G2 manifolds, is difficult. All right. So if we talked about masses from a different point of view, which is mostly EFT with some string inspiration, you might ask the question, OK, so suppose that we have a realistic theory, so it's got to contain the standard model, and we have a theory with an axion in it. Well, if you want to talk about effective field theory, you have to talk about all symmetries. So there may be more symmetries than this, but at the very least, if this is true, we're going to have G standard model and some axion shift symmetry. This is just the axion shift symmetry inherited from the p-form symmetry in higher dimensions. OK? So I'm after masses. So if I'm after masses, I need to talk about effective scalar potentials. Right? OK? And what I need to do is I need to write down some v for the axion that is consistent with all symmetries of the theory. There's some prefactor A that in effective field theory would be order 1. In string theory, it's going to be instanton suppressed, and I'll say a little more about that. And the shift symmetry, we need to respect the shift symmetry of the axion up to an overall discrete breaking. These cosines are the types of terms that you're going to get from the instantons in the effective action. But the other thing that we haven't talked about is that we're not talking about all effective operators consistent just with the axion's shift symmetry. We're also allowed effective operators that are consistent with G standard model. And there's a scalar field in the standard model that could potentially appear in these effective operators. So it needs to be gauge invariant, so you can't just write h dagger. You need to write h dagger h to the n. H is the Higgs, over lambda to the 2n minus 4, where lambda is some cutoff in the theory. And this is the effective operator that you have in the game. So a nice thing about this is that if you haven't, and I should say, part of the inspiration here, so in effective field theory, this is just allowed. You can ask the question, does string theory actually give rise to operators heuristically of this type? And I'll say that this non-trivial part, there were some instanton papers in type 2A, but also applies in other contexts in 2006. This was Blumenhagen, Svedich, Weigand, and also Ibanez Aranda. And Katru et al. I forget the other. Katru, McGreevy, Florea, and Salina. But that basically said not only can you have these moduli appearing in the instanton prefactor, but you can actually have fields, chiral supermultiplets, that are charged under some gauge group appearing. Of course, the overall combination has to be invariant under the standard model gauge symmetries in there, but this is possible. And what this can do, from the point of view of the effective potential, is give you operators that involve the Higgs. And if you're in a SUSY context, it'll be HU and HD, and there will be tan betas. But I'm just going to talk at this level for now. And so what happens when you work this out is that MA squared, that mass of the axion, is A, expanding out this potential. So the Higgs VAV is going to give you a lambda electroweak, the electroweak scale, over lambda to the 2n, lambda to the 4th over F squared. I'm massaging it appropriately. And therefore, MA is going to be root A lambda electroweak over lambda, again, writing it in a good way. That will be, in my opinion, illuminating lambda electroweak over lambda. But then there's an overall lambda here, which is going to cancel lambda over F. And so you guys can work that out. Yeah, that cancels against that. You guys can work that out, but you might ask, if this is the effective mass that you're getting from this effective operator approach, where you've allowed for the possibilities of the Higgs and the potential, what sorts of masses do you get? So for values of these parameters that are at least in some sense reasonable in string theory, what you might do is take the cutoff and the Axion decay constant, both to be near the Planck scale, or maybe you choose gut and the values change a little bit. And if this is the case, then the Axion mass is going to look like lambda electroweak times the hierarchy to the n-1. And this look like is important because this is up to this factor, this important factor that can be instanton suppressed in string theory. So basically, I just plugged in here. And what you're going to get when you take lambda to be Planck scale, this is literally the electroweak hierarchy that's appearing in here. And so one way to think about it is, depending on the value of n, the Axion mass is going to be the electroweak scale times some appropriate numbers of powers of the hierarchy. And so if you ask what sort of benchmark spectrum might you expect, and I will try to be clear about all of the caveats. OK, so here's the n equals 0 case. The Axion mass, this is ma, will be at m Planck. At n equals 1, this will be at lambda electroweak, which is 100 GeV. N equals 2, 246, but that's close enough for this. And n equals 2 will give you 10 to the minus 5 eV, which is about the neutrino mass scale. And n equals 3. N equals 3 is 10 to the minus 21 eV, which is a scale that is these days called the ultralight scale. OK. Now, the thing that's a little bit of a kludge here is that in effective field theory, you have your effective operator with some coefficient. You expect it to be order 1. But we know in string theory that these are actually going to be coming from e to the minus t. The vev of t, where this is some Kähler modulus, in 2b, it's controlling the size of some cycles in the extra dimensions. And so this a will give you this instanton suppression. So this is not necessarily the way to think about it, because there is this critical factor here. But basically, this is one way that I think about it, is that there are sort of these benchmarks, and then instanton suppression, if you have lots of axions, can kind of come in and fill in the spectrum. OK. And of course, the instanton suppression can be very large. So it could be that you're in this case, and the instanton suppression is so big that you come down to here. There was a paper that I'll mention in a second that did this last fall. Yeah?
What do you mean by reasonable string theory?
Yeah. So for example, when you actually, first of all, we expect the ultraviolet cutoff of the theory to be string scale, which we're typically expecting to be up at gut scale. This is the thing that you may be a little less familiar with. Axion decay constants in string theory can have a spectrum to them, but typically the spectrum is centered somewhere around the gut scale, or maybe even up a little higher. This has been studied a lot recently because people were interested in this being large or super Planckian for the sake of large field axion inflation. But it turns out that that's actually very hard, and this usually likes to be a little bit lower than the Planck scale. So when people actually study these things concretely, they often find that you have sort of gut scale or a little below Planck axion decay constants with some distribution, because you have lots of axions and lots of axion decay constants. Yeah. Did that answer your question? There's someone else who had her hand raised right behind you. OK, great. So that's what I mean. OK, so great. Cool. All right. I have like 2 more boards on axions. So this is just the basic formalism. And they're everywhere in string theory. And there's a whole group of people that are spending a lot of time thinking hard about the cosmological implications of axions. I recommend papers, for example, by Joe Conlon and also by the David Marshes. There's 2 of them, both of whom work on Axion Cosmology. including a review by Marsh that is a good review. And just to emphasize, many cases in which you've heard about axions are in the context of the specific axion, the QCD axion, that can be used to solve the strong CP problem, which I'm not going to talk about. These string axions are not necessarily those. In fact, at most one of them is those. And there are all of these other guys in the game that can change cosmological stories and either be interesting or kill the theory depending on context. Okay. Okay. So let me start here, actually. Okay. So Axion Cosmology. This is about the remnants. This was all about formalism until now. How to think about axions in the context of string theory. We talked about where they come from, how they're everywhere, how there are typically hundreds or thousands of them, where their masses come from, what the full calculation would look like, and if you thought about it from an effective field theory point of view, what might that look like? And so Axion Cosmology, you can ask, if you excite these in the early universe, what can happen? So here I'm going to have an axion phi. And in an FRW background, the equation of motion for an axion is phi double dot plus 3h phi dot plus ma squared phi equals 0. And of course, h is the Hubble constant, and it's h of t, which is a dot over a. And this implies that your Axion cosmology can be time dependent in interesting ways. So there's two basic cases. In case one is times in the expansion of the universe where the Hubble factor is greater than ma. If this is much, much greater than ma, this looks like a friction term. And this friction term is going to freeze. Hubble friction is going to freeze phi. OK? W phi in this case. So W, remember that in FRW, we talk about pressure and energy density of various components. P is the pressure of a component. And there's the energy density, and they're related by the equation of state parameter W. W phi is -1, which implies that in this case, the axion behaves like dark energy. Okay. The other case is if Hubble is less than the mass, then you can ignore the middle term, and this just looks like a simple harmonic oscillator, and you get oscillations of the axion field. Okay. In this case, W phi is equal to 0. One important thing about this is that depending on W, it tells you how the energy density of that component scales with the FRW scale factor. So rho of phi in this case goes like 1 over a cubed. And in particular, this axion in this case is behaving like cold matter, like dust. Okay. Okay. And so you can then ask the question, is this dark matter? In particular, you can ask for what values of the mass is it allowed to be dark matter? Well, by the time that dark matter comes to dominate the energy density of the universe, which is critical for structure formation, you had better have already entered this phase where the axion behaves like dark matter if it's to be a large component of the dark matter. This means that you need to enter this phase where h is less than ma before matter radiation equality. And h at matter radiation equality is like 10 to the minus 28 eV, which it would imply that m phi is greater than or equal to 10 to the minus 28 eV. Okay. And for more on this, I highly recommend David Marsh's review, Axion Cosmology. OK, so that can't be the end of the story. You have to ask, what is happening that you get some non-trivial energy density at late times in the axion that could let it be the dark matter, and even at intermediate times? And so the basic idea is that Hubble starts above the axion mass. The axion is displaced from its minimum with some ideally order 1 displacement. And then, as the universe expands and Hubble gets to be less than the axion mass, the field starts oscillating. It behaves like cold matter. And eventually, there's some relic abundance. And the work in the case of the QCD axion in the 70s and 80s led to this production mechanism that is called the misalignment mechanism. And the misalignment mechanism gives you some relic abundance for axions. And of course, there's a particular value that it has to be if it's going to be the dark matter. All right. Great. So I think for what I'm going to write, I can even just write it here. So when you do that, so this equation is taken from the paper of Hui, Ostreicher, Tremaine, and Whitten from last fall sometime. I think it was October. And they were interested in ultralight axion dark matter. And the relic abundance, written in a way that is amenable to thinking about string theory, is something like 0.7 squared times 0.1 times the axion decay constant over 10 to the 17 GeV. This is the relic abundance you get from misalignment production, MA over 10 to the minus 22 EV to the 1/2. And just to stare at this equation, so this equation, if this axion is all of the dark matter, it has to agree with the observed dark matter relic abundance, for example, from Planck. And the number for omega h squared observed is 0.12. So this is some order 0.1 number up here. And so basically, this way of writing the equation is telling you that if you have sort of a 10 to the 17 GeV axion decay constant, and an axion mass of order sort of 10 to the minus 22, 10 to the minus 1. There's wiggle room, of course. But an axion mass sort of on this scale, then this is giving rise to the observed dark matter relic abundance. And part of the reason that these authors were interested in this issue is that in the astrophysics community for a number of years, there's an idea that has been pursued called fuzzy dark matter. And in this context, and in other contexts, they were asking, can an ultralight boson that's very, very light at this scale be the dark matter? And so this paper was interested in thinking about, in addition to astrophysical effects that are very important to consider, was also interested in thinking in part about UV completions from string theory that could give rise to such light axions. And there's a number of things there astrophysically that people will debate whether they should be entering into our story about dark matter now. One is called the core versus cusp problem. There's issues about satellite galaxies that are interesting. But some of the astrophysical questions are prompting some people to think about dark matter in different ways. And there's a question of whether it's at all natural to think about in the context of string theory. And that's a very interesting question. And the answer, of course, isn't totally settled. And there's lots of issues to take into account. But this is the basic story, that string theory gives you lots of axions no matter where you are. There's a full story that could lead to moduli stabilization and concrete computation of axion masses. But if you take a simple if you take a simple approach to thinking about the effective operators, there are ways to get axions sort of in the range that is interesting from this point of view for this ultralight axion dark matter. There's lots of other things to think about with axions, too, in the context of string theory. This is not the only one, but it's interesting. And can axions be the dark matter is a good question. Can they be the inflaton? Do they give rise to large field inflation? If they're too light, can they give you too many light degrees of freedom? And can it rule you out based on Planck observations of delta n effective? So that's really all I have to say about axions. But they're ubiquitous in string theory. They're in every context. And the natural question is whether they should really enter into how we think about cosmology, in particular particle cosmology, and also whether or not it might force us to into sort of a different paradigm and to think a different way. So that's all I have to say about axions. But any questions before I switch gears? Yeah?
So to have so many axions,
we do.
I suppose that the QCD axion is a real thing. Why am I only getting one of these sort of showing up coupled directly to the standard model? Why don't a bunch of them?
So when you work out the effective action, in the context of the QCD axion, the question is which linear combination of those AIs is going to be the thing that actually couples to GQCD wedge GQCD in the effective action. So it so happens that one of them, one linear combination, it's not usually one of the basis elements. It's usually some linear combination that couples to that particular field strength. Good question. Yeah?
Can you comment more on these really light axions behaving like dark energy?
Oh, I don't know that I have a whole lot more to say about it. Marsh's review talks about it, but the basic idea is exactly that if the equation, in this regime where h is greater than ma, the equation of state is -1. And it's presumably, if you have too much of them, where'd you go? There you are.
It's like inflation, isn't it? I mean, this is kind of the situation where the inflaton drifts into its...
That's right.
death.
That's right.
So I should think about this more as the inflaton.
I think there are constraints also from it. So it can be the inflaton. That is the main thing that people study axions for in string theory. I think that's probably safe to say. But I think there are also other constraints coming from considerations of dark energy. I'm not too familiar with them, so I don't want to elaborate. And yeah.
So is there anything that happens when h equals ma, or is that like not? I think these are greater than or less than, I don't know.
Yeah. I mean, maybe I'll use the word that Tom used, poetry. So when you have these transitions that can happen, I mean, it's simpler in this case because QCD is more complicated than a simple harmonic oscillator by a long shot. But it's frozen in, and as they become comparable, it's going to start to oscillate, and you're going to have more and more underdamping until, in the case where h really goes to 0, it's just going to be going back and forth. The poetry of the in-between region. I like that phrase. Yeah. All right. So in the remaining half hour, I want to talk about string consistency conditions and beyond the standard model exotics. So yesterday, I talked about dark gauge sectors, which might be very, very, very hard to ever observe. Sadly, that would be in perfect agreement with current dark matter observations. But that, of course, could change. But if that were true, we may not really ever know it, which would be a sad situation to be in. Axions are more observable. That was why BICEP was so exciting. Well, they wouldn't be directly observable as axions, but some of the signatures of large field inflation that come about in the context of axion inflation would be observable. And now we're going to talk about something that's, if the particles are light enough, are extremely observable. Because if there are chiral supermultiplets that are charged under the standard model gauge group, or MSSM gauge group, and they're light enough, they're going to couple to the standard model gauge fields, of course, and probably other things in the superpotential, and give rise to potentially observable signatures. And of course, at LHC, there are groups that are looking for exotics all the time. That's dry. I'll go down there. So, all right. The context here is weakly coupled Orianifolds But again, this is a story that has been around for many years. Heterotic orbifolds, smooth heterotic, etc. You're typically getting beyond the standard model exotics. This is just a dumb picture that I like to use to think about this. If you have a dartboard and a bullseye, right? And you're doing string compactifications, and maybe the bullseye is the standard model, and here is the MSSM. When you do concrete compactifications, it is true that sometimes you get the spectrum and gauge group bang on. That's possible. But over the years, what we've also learned is there's lots of near misses, right? Where near miss means maybe I've got the MSSM spectrum, but I've got an extra vector-like pair of chiral supermultiplets that are charged under the standard model gauge group. And there are all these near misses. And from a particle perspective, you can ask, maybe this doesn't mean anything, or maybe one takes something from it. But there's a question. Maybe we have the wrong bullseye. Okay. From a formal point of view, there's an interesting question of why do you get those exotics? Okay. And so what I want to talk about is how consistency can imply, maybe with a question mark, beyond the standard model exotics. Okay. A few comments. In general, these are quasi-chiral exotics. What I mean by that is they're vector-like with respect to the standard model, but chiral with respect to some other symmetries, so that in particular their bare mass term in the superpotential is forbidden, just like we want the mu term to be. This arises in other contexts, and again, depending on the mass, these things are ultra observable. OK, so again, I'm starting with formalism, because string remnants are about things that the UV theory gives you. So we have to talk about the UV theory. Here I'm going to be in 2A with intersecting branes, in particular D6 branes. And the setup is that I have some Calabi-Yau threefold X and an anti-holomorphic involution. Sigma is a map from X to X. This is a CY3. And what this is going to give is O6 planes on the fixed locus, sigma fixed, which I'll define to be pi O6. And the homology class of pi O6 sits in H3 of XZ. Okay, sorry that got off the board a little bit. But, of course, as Timo already talked about, you can't just insert branes into compactifications willy-nilly, because there's a Gauss law constraint. O6 sources are R fields. And if you have sources, the Gauss law implies you need sinks. Okay. So in particular, what I'm going to do is I'm going to introduce D6 branes to cancel that charge. I'm going to have NA D6s on pi A. These guys, their homology class is sitting in H3 of XZ. Okay. There's Orianifold image branes. NA D6 on pi A prime. And finally, and very importantly, there's a tadpole cancellation condition. This is just the Gauss law. This is derivable from, for example, 2B supergravity in the presence of these sources. And the condition is sigma sum over A NA times pi A plus pi A prime is equal to 4 pi O6. Right? And this is where the magic comes from. And that's the consistency condition. And I'm going to give this a name. This is going to be star 1, apparently. Not quite dry. OK. There it is. OK. And similarly in type 2B, there are the effects that I'm going to tell you about here. There are D7 and D5 brane Gauss laws that come into the game to play the same role that the D6 case is here. Just that the D6 case is cleaner. OK, great. So that's fine. But what about the physics? D6 stacks imply gauge sectors, right? All right. So G is going to be a product. I'm going to not consider SOs just for simplicity, of UNA. NA D6 branes will give rise to a UNA gauge group. There's going to be matter. The picture is this, that you have some D6 stack carrying UN and some other D6 stack carrying UM, and they intersect. And at the brane intersection, which is a point in X, you have matter from open strings stretched between the two branes. OK? But this matter, what you want to know is, in particular, what is the chiral index of this matter? So by chi of r, I mean the number of chiral supermultiplets in the representation r minus the number of chiral supermultiplets in the representation r bar. OK. And moreover, if I'm talking about r equals n, what I mean is box n, the fundamental of SUN. And so basically, given a concrete compactification where you have introduced all of these D6 stacks wrapped by, that are wrapped on these pi a's and the O-fold, which is on this pi O6, you can just compute the spectrum. And it's this. So the number of bifundamentals of UN and UM with a bar is pi n intersect pi m. This lives in Z. And there's other guys that appear too. You can also get symmetric tensors and antisymmetric tensors and appropriate chiral indices. These involve the orientifold. But the exact, this is a function of pi O6. The exact expressions don't really matter now. The basic point is that I can compute the chiral spectrum, the massless chiral spectrum of the fields charged under these gauge groups in this context. OK, good. I'm not going to say much about U1s in this case, but there's trace U1s inside these UNs, and linear combinations of them can be massless. OK. OK. So let's talk about matter constraints. So this is the basic setup. Before I switch gears and talk about constraints on the matter, are there any questions about the basic setup? OK. 2A intersecting branes. All right. So constraints on the matter. Pardon? Oh, yeah. I mean, so definitely I am in type 2A, which is a weakly coupled orientifolds, generally speaking, are a small corner of the landscape. But nonetheless, some of the properties of these constraints that I'm going to talk about are more general. Yeah, absolutely. So I'm working in a weakly coupled corner where I can control everything, and we're going to get a little bit of a surprise that should generalize beyond this corner. But that's absolutely right, Miriam. OK. So in particular, these things arise in type 2B, and they almost certainly also arise in F-theory. All right. So what do I have? Oh, and I gave these a name, too. These together, all of these ideas are going to be star 2. What I have is star 1 and star 2. Star 1 is homology equations. That's an equation on homology, the Gauss law, for the sake of consistency of the theory. You don't have a consistent compactification unless star 1 is satisfied. That's star 1. And I also have what I'll call an integer equation for matter. And I also have gauge sectors from ND6 on pi n. OK? And you can ask, given these ingredients, can you relate them to one another? And the answer is yes, because if you take this homology equation and you intersect it with the D6 branes wrapped on pi n, you'll get an extra constraint. does there exist a relation, a simple version of this relation? Let me ignore orientifolds for the moment. In the absence of orientifolds, this equation is sum na pi a equals 0. Star 1 becomes that in the absence of orientifolds. And when I take this and I intersect it with pi n, what I get is that 0 is equal to sum na pi n intersect pi a, which is sum na pi box n box bar a, which is chi box n, and that has to be 0. And the more complicated version gives a similar constraint. And this constraint is chi box plus of this un plus n minus 4 chi antisymmetric plus n plus 4 chi symmetric equals 0. And I will call this T sub n. Okay? So this is a constraint on the chiral spectrum of the low energy theory that is necessary to have a consistent compactification because it's necessary for the Gauss law for the D6 branes to hold. It's not sufficient because there's more information in an equation in homology than there is in an equation in integers. But it's necessary. So how do I understand this constraint? We have this constraint, Tn equals 0. And most of this goes back to some very beautiful work in the early 2000s by various people doing intersecting branes, including Miriam and company, and Luis Ibanez and company, and who am I probably forgetting? I'm forgetting others. There's lots of beautiful papers on this idea. Yo, of course. That's exactly what I was going to say. Blumenhagen et al. And basically, if we want to understand this constraint, let's just note this simple version here. The number of fundamentals minus the number of anti-fundamentals is 0. We know what that is. For n greater than 2, this is precisely cubic non-abelian anomaly cancellation. So string theory gives you low energy sectors that do not have cubic non-abelian anomalies, as you would hope. For n equals 2 or 1, these are, in a sense, stringy constraints, ones that at least aren't obvious from a low energy point of view. In particular, I always get this question when I'm talking to people about this. This is not the Whitman anomaly. Who remembers what the Whitman anomaly is? Yeah, exactly. So in the simplest case, it's a Z half. You use the notion half. It's a Z2 condition that's an anomaly cancellation condition. So the paper is called the global SU2 anomaly. And what he proved is, for example, in SU2 gauge theory in 4 dimensions, if you have an odd number of Weil-Fermion doublets of SU2 and that's it, that theory does not exist. It's inconsistent. You need an even number. This is called the Whitman anomaly. There's generalizations. But this is not the Whitman anomaly. This is some exact equation. This is not a Z2 equation. And so let me tell you what this imposes. So why, string theory, are you giving us this constraint? So it's totally understood in the n greater than 2 case. And there's a couple of things to say in the t2, 1 equals 0 case. So it turns out that this is necessary but not sufficient. Such a long thing to write out over and over again. For both D6 Gauss and U1 anomaly cancellation. Okay? I'm running out of room, so I'll write this here. It's also necessary and sufficient. Actually, this deserves further comment. It's clear that it's necessary for D6 Gauss because that's where I got it from, star 1, right? So it turns out, and I think this goes back to papers of Luis and Fernando Marchesano and company. Yeah, that's right. And maybe others did it too. What they showed is that when you study U1 anomaly cancellation in intersecting brane models, the Chern-Simons terms do some of the anomaly cancellation for you. There's tree-level effects where there's an axion propagating. Green-Schwarz does some of the cancellation for you. But there's some remnant piece of the would-be anomaly that is canceled by the tadpole condition. And that's what this is. So you need this together with the appropriate structure of Chern-Simons terms to have U1 anomaly cancellation. And it's also necessary and sufficient for no SU n plus 2 cubed anomalies. Maybe I should say n plus m. If you nucleate a brane-anti-brane pair, in particular m d6 and m anti-d6, on cycles, on homologous cycles. So what does that mean? It means that you might have this SU2 gauge theory living on 2 D branes in a 4-dimensional theory, but that vacuum could be a low-energy state that could be arrived at if you were to add m d6s and anti-d6s. So put m d6s on top of the 2 d6s and put m anti-d6s a little bit away. There's going to be a force between them. It's not BPS. They're going to annihilate. Tachyon condensation is going to give rise to the theory that you started with. But prior to that annihilation process, it looks like you have more than the original 2 d6s on top of each other. And to not have anomalies in that theory, this constraint is necessary and sufficient. And so it's kind of a nice story, because one of the beautiful things about string theory is that gauge sectors aren't just gauge sectors. Gauge sectors are carried by charged objects. And if charged objects can pair produce, just like electrons and positrons might pair produce, you might ask, in the unstable states after some pair production process, or maybe you have the unstable state to start with, and you're zooming towards an annihilation that's going to give you a vacuum, even in those unstable states, string theory is imposing its own consistency. Okay? So this is a beautiful constraint, and I think there's many ways to understand it. And it's not something that you would have perhaps come up with if you were thinking from the bottom up. It's something that automatically comes out of thinking about string constructions. And in this particular context, you can derive it in type 2b also. But because of the way that this happens, it's really related to consistency. I think there's plausible evidence that it also exists outside of these weakly coupled limits. And in particular, it should exist in F theory.
So I must have missed something.
Yeah.
You started off deriving these things from Gauss's law, but if I have d6 anti-d6, I hope never violate Gauss's law. So I missed an extra input here.
Yeah. The extra input is that imagine that I have some vacuum that satisfies Gauss's law with a bunch of d6s, no anti-d6s anywhere.
Yeah.
That Gauss law constraint, that equals 0 in the Gauss law. I can add a brane-anti-brane pair on the same cycle without changing that equation at all. It's taking this original constraint, star 1, and adding 0 in homology. Right? So for any given star 1 constraint, there's not just the stable vacuum that you would consider. There's also an infinite tower of brane-anti-brane pairs that you could add to the theory that would effectively just be adding 0 to this equation. But the point is, those unstable states had better be consistent as well.
I just don't see how they'd be inconsistent. Okay.
OK, good.
I actually think about it.
OK, cool. So they're not, part of the point is that in string theory, they're not inconsistent. Okay. All right. One thing that I should say is that part of the backdrop here is that in SU-n gauge theories in 4 dimensions, the anomaly cancellation conditions on SU2 gauge theories is fundamentally different than the anomaly cancellation conditions on SU-n greater than 2 gauge theories. So that's part of the story that's going on behind the scenes. All right, but to save time for questions, I basically just have one more thing that I want to show you. So the remnants, this is the formalism. I'm going to show you a table with remnants, and then we can talk about them and take questions. If one was to consider how might you possibly embed the MSSM in string theory in this type 2a context, you have to satisfy these low energy consistency conditions T2 and T1. And you might consider all ways that you could write down a string spectrum that could potentially realize the MSSM fields. You would then ask, does that set of fields satisfy these conditions or not? And then if it doesn't, you can throw it away, or you can say, I can add fields to the theory to make it consistent. And if you do that systematically, what you will get is beyond the standard model exotics. This is one way, sort of mixing top-down and bottom-up, to see how you can get beyond the standard model exotics out of string theory. If you started purely from the top-down, I'm willing to bet that you could, in the compactifications where you're getting, where you're getting exotics, I bet you can see in certain cases that if you remove them, you're going to be generating some inconsistency in the theory. So all I want to do is show you what sorts of exotics you get. So this is in a systematic bottom-up analysis that satisfies these T2 equals T1 constraints. How do I get this thing down here? No? He has headphones in. Tom, do you know what the switch is?
How do you drop the screen?
Thank you. OK.
Which ones do you want to know?
I just need one.
Just need one.
Just need one. OK. This is not complicated, so I just need one. So in these setups, it's a tedious calculation, but you can be super systematic about it and just ask what sorts of exotics do you get, and how many of them are there according to their standard model representation. Oh, it's going to take a few minutes.
Yeah.
Oh, not good. Maybe I should ask at this point, are there any questions? That's coming up. All right, there it is. That was the fastest few minutes of my life. All right. All right, so this is in a systematic bottom-up analysis. This is generating, I think the number is something like 90,000 models or something like that. And this is the full table of exotics that you get out of these sorts of constructions. I'm going to try to not jump too much. But on the left-hand side, you have the standard model representation of the exotic fields. You have the number of times they appear across the entire model set and some various subtractions that lead you down to, after those subtractions, some final counts. You'll note that the things that have conjugate pairs in there that would form vector-like pairs are appearing with appropriately mirrored numbers. For example, in the third and fourth line, 38,814. Those are fields of standard model representation 1, 2, plus or minus 1/2 that are coming in pairs. These would behave like vector-like leptons. Depending on how they couple in the superpotential, they would behave like extra Higgs pairs. And there's this whole set of things that can happen. This is just in this one particular context in type 2a and weakly coupled type 2b. In other contexts, you might get a slightly broader set of reps. But the basic idea to take away from this is that not only can string consistency conditions force exotic matter on you, but also sometimes there seem to be certain preferences for certain types of representations over others. And this is interesting in part because if these are light enough, which there's a symmetry protecting their masses, if these are light enough, for example, if the same effect that generates the mu term at the electroweak scale also generates these guys, you would expect these pairs to be electroweak scale. And those are potentially discoverable at LHC, although in the case of exotics that aren't colored, it's significantly harder to find them. That's all I really have to say about these. I can take questions on them, but maybe since there's only a few minutes left, I'll conclude and then take general questions, including on this. So the basic punchline of all of this is that string theory does many, many wonderful things for us. Mirror symmetry is fantastic. ADS-CFT is beautiful. There's all sorts of formal things that we work on, most of us, all of us, myself included. But the question of whether our world is a string compactification is a different question. And it's a hard question because the landscape is big. But regardless of what we mean by landscape, what often happens is that there are low energy remnants, low energy degrees of freedom that are remnants of the ultraviolet theory that might change how you think about particle physics or cosmology. And it is an important thing to try to understand them as generally and in detail as possible. The three that we talked about were large gauge sectors coming from this ensemble of 4/3 times 2.96 times 10 to the 755 F theory compactifications, which could potentially give rise to either dark glue balls that are the dark matter or constraints from dark sectors that oversaturate the dark matter relic abundance. There's axions everywhere that could be interesting from the point of view of inflation, from the point of view of dark matter, et cetera. And then there's also these beyond the standard model exotics that appear quite generally. The one thing that I didn't get a chance to tell you about was moduli and their potential importance, but that's a longer story. So, all right, thank you very much.
About your long story, which you didn't talk about.
Oh, yes.
So surely, I mean, when you're talking about these dark sectors, that has to be in the context of this particular point on the landscape that we happen to live in.
Oh, absolutely.
Right. So that means that you have to find a model which has the standard model.
Absolutely.
Right. And where all the moduli are stabilized, the cosmological constant is 0 or close to 0.
That's very hard, but yes.
So that's a long list of stuff, and so those are additional constraints which you didn't consider.
Absolutely, I didn't take them into account. So the question, I mean, it may be the case that in some of these, well.
So maybe it's the case that none of these are relevant.
It may be the case if you condition on that. In particular, the CC and the standard model are particularly pressing issues. It may be the case. I don't necessarily have anything concrete to say about that, except that, you know, I think it is believed by many people, myself included, that, for example, in the case of axions, we're going to get some number of them.
But axions, yes.
Yeah, I think, yeah, absolutely. So if there was some cosmological dynamics or some selection mechanism that meant that the standard model was only appearing in these sectors that don't have large gauge sectors or these cases without exotics, absolutely. I totally agree. That'd be fascinating. I just don't know of a reason why that would necessarily be the case yet, but it could be the case. As far as the beyond the standard model exotics go, in a sense, as you know, those often are arising because people are looking for the standard model in string theory, and it's kind of a close but no cigar phenomenon. And I guess what I'm saying is that the no cigar part of that can be interesting and detectable.
Well, there's also, maybe if I could put
Sure, yeah.
There's also an argument that if those are chiral superfields, even after modular stabilization, chirality is sort of expected to be protected in this charge sector.
But I absolutely am in agreement with you.
With three families of quarks and leptons,
Yeah.
even after modular stabilization, the hope is that the fact that you still have three chiral families is expected to be protected from effects of modular stabilization. I'm sure you've heard that.
Yes.
Yes.
Anyway.
Yeah, Lance.
So, I mean, for these things to be light, they're vector-like under the standard model. They're chiral, maybe under some extra U1.
Exactly.
Does that mean, they expect to find extra U1s too?
Yes, so in many cases, the U1 is anomalous up at string scale. And, well, they don't have to be. They can also be light Z primes.
If it's anomalous, is the thing still protected, or is it likely to get a mass that's much higher than the electroweak scale?
It could be generated by instantons, for example, but then there will be instanton suppression. The case that I'm most familiar with is that those operators that are forbidden by an anomalous U1 are generated by an instanton. This is a story that was studied in real depth about 10 years ago. And in that case, yeah, it may be heavy, but there is instanton suppression that could make it light. More generally, I mean, the way that I view it is more or less that the solutions to the mu problem are basically in the game here as the sort of thing, whether it's the same effect that solves the mu problem or that type of effect but in a different incarnation. These questions are very analogous to the mu problem, as you know. So yeah. They may not be light, though, absolutely. Yeah. But there is a symmetry, which is much better than not having a symmetry and having them up at Planck. Yeah?
When we do model building with intersecting grains in type 2A,
Yeah.
for example, in a easy case of like Torai or Befolder,
Absolutely.
there is some extra constraint that I've never understood, which is called the K Theory Constraint. Is this the same thing you're talking about or not?
I should get my iPad off there so you guys don't see my Slack messages. But sorry, the K Theory Constraint.
Yeah, is this the same thing you're talking about?
This is maybe there's some relation, but from the papers that I know, which is, as you know, papers by Angel, the K Theory Constraint is often arising in context of things like the Whitman Anomaly. The K Theory Constraint is sort of imposing these sort of discrete anomaly conditions that are Z2s and the like. So for example, the K Theory Constraint can arise when you have SPN gauge groups on D3 brane, well, I don't know about it in the D6 context, but on D3 probes of 7 branes, for example. And I don't think that they're necessarily related, but I haven't thought that much about the K theory constraints.
Actually, pretty much very close relationship, so in other the sense to put it.
So they may be related, but they're not the same because this is not a discrete constraint. This is an equality.
No, okay, I'm sorry, but there's the discrete constraints on having even number of certain representation under
Oh,
SP,
absolutely.
which does happen in
Absolutely.
global constructions, right? So SPs are
Right.
especially
Right. Those discrete constraints are arising from K theory constraints from the string theory point of view. Those are different than the constraints I'm talking about here. Yeah, absolutely.
The bottom line, are we missing something or are we not missing something if we just do this kind of analysis? Maybe we want to include this extra condition too about nucleating brain, anti-brain. If we do that, is that enough? Or do I have to run K theory too?
For the full construction, if you really want a top-down model and you don't want to be working from the bottom up talking about potential string embeddings, you need the full thing.
So you're saying the full thing's not contained in this?
Exactly. This is necessary but not sufficient for the full thing. But part of the reason that it's powerful is it gives you a necessary constraint that doesn't require that you learn K theory. Right.
Is there a simple example where what's the simplest example where I would have needed K theory but could not have deduced the right constraint from these kinds of considerations?
Where you would have needed K theory. I would have to think hard about that. I don't know of an example off the top of my head. But the point is that these constraints are low-energy four-dimensional constraints, whereas K-theory constraints and these Gauss's laws are something really about the higher dimensional theory.
Sure, Gauss's law I'm okay with.
Yeah.
I understand that.
I would have to think more about the K-theory constraint. Yeah, good question. These things are not trivial.
certain, discrete versions.
Oh, absolutely.
That's not for
Right.
condition, right?
But the simplest version that tells you when the K-theory constraint is important, I don't know. Yeah.
But those are really global.
They are. They're global things in the top-down, fully compact context. Ed's paper on K-theory and D-branes probably has lots of simple examples that would illustrate this. Yeah.
Maybe that's a good point to thank Jim for the set of two very intriguing dynamic lectures. Thank you.